Imagine seeing our solar system from several light years away. The sun would still shine, but its light might look different. Around it, countless artificial objects would move through carefully planned orbits. Some would collect sunlight. Some would process raw materials. Others would manufacture new machines or transport cargo between industrial regions. Vast radiator systems would release unused energy back into space as infrared heat. Together, they would form something larger than any engineered system humanity has ever created. Yet there would be no solid shell surrounding the sun. Every component would remain an independent spacecraft, factory, habitat, collector, or computing platform following its own trajectory. This is the idea of a Dyson Swarm. And if a civilization were ever to operate on the energy scale associated with a Kardashev Type 3 society, mastering infrastructure around individual stars could be one of the crucial stages along the way. The question is not simply whether we can imagine a Dyson Swarm. It is what building one would actually require. When we imagine extremely advanced civilizations, it is easy to jump straight to the largest possibilities. We picture societies moving between millions of stars, engineering entire worlds, constructing enormous observatories, or spreading technological infrastructure across the galaxy. But between a civilization like ours and one operating at galactic scale lies an enormous missing stage. Before any society could make extensive use of a galaxy, it would first have to become remarkably capable inside its own planetary system. It would need access to resources beyond its home world, large-scale industry in space, highly automated transportation, and eventually the ability to intercept a meaningful fraction of the energy produced by its own star. That is where the Dyson Swarm becomes important. The Kardashev scale is often summarized as Type 1 for planetary scale energy use, Type 2 for stellar scale energy use, and Type 3 for galactic scale energy use. These categories are broad conceptual markers rather than precise engineering milestones, but they illustrate the extraordinary difference between the energy available to a civilization confined to one planet and the energy produced by an entire star. Humanity currently uses only a tiny fraction of the solar energy reaching Earth, while Earth itself intercepts only a very small fraction of the sun's total output. A civilization moving towards stellar-scale energy use would have to change that relationship. Instead of relying mainly on one planet for energy, raw materials, manufacturing, and population, it could begin treating the entire solar system as an interconnected economic environment. The first stages might look surprisingly familiar. More solar power satellites could appear around Earth. Long-duration settlements might develop on the Moon. Asteroids could provide metals and water. Large structures could be assembled directly in orbit. Solar-powered industrial facilities might operate far from Earth, while free space habitats gradually become practical. None of those achievements alone would constitute a Dyson Swarm. Together, however, they could establish something much more important. An industrial system that no longer requires every important component to be launched from Earth's surface. That is a critical threshold. Earth is a difficult place from which to export enormous quantities of material. Its gravity is strong, its atmosphere complicates launch, and its biosphere is something a technologically mature civilization would presumably want to protect rather than convert into a giant industrial extraction zone. A true Dyson-scale construction program would therefore need to obtain most of its mass from space. That could mean resources from the Moon, near-Earth asteroids, the asteroid belt, Mercury, and perhaps bodies much farther from the Sun. But finding material is only the beginning. Space industry would need to refine ores without Earth's atmosphere, infrastructure, or oceans. Mining equipment would have to function in extremely weak gravity. Factories would have to manufacture structural components, sensors, electronics, propulsion equipment, mirrors, solar collectors, and thermal systems in environments where a human technician could not simply walk outside with a toolbox. The real Dyson Swarm challenge is therefore not the construction of one gigantic object. It is the creation of an entire industrial ecosystem. A mature swarm might contain mining stations, refineries, orbital foundries, cargo vehicles, solar collectors, communication networks, repair systems, navigation infrastructure, habitats, computing platforms, and enormous radiator surfaces. Every part would support other parts. A collector could power a refinery. The refinery could provide metal to a manufacturing plant. The plant could produce another collector. That collector could supply energy for additional machinery. If enough of this process became autonomous, the solar system's industrial capacity could begin expanding without requiring a proportional increase in launches from Earth. That feedback loop is potentially transformative. At first, Earth could remain the center of technological civilization. Later, an increasing percentage of raw materials might originate elsewhere. Eventually, much of civilization's energy production, computation, manufacturing, and perhaps even population could exist beyond Earth. The solar system would cease to be mostly empty territory occasionally visited by spacecraft. It would become infrastructure. The sun would sit at the center of an immense distributed economy. Seen this way, the traditional image of a rigid metal sphere becomes almost beside the point. The practical questions are different. How many collectors are needed? What should they be made from? Where should they orbit? How much material would the system consume? How would enormous numbers of spacecraft share orbital space safely? How would energy move between facilities? How would the civilization reject waste heat? And how could a technological network of that scale continue operating for centuries or millennia? Those are the questions that turn the Dyson Swarm from a science fiction illustration into an engineering thought experiment. And before addressing them, one misconception needs to be removed. A Dyson Swarm is not the solid Dyson sphere familiar from popular culture. Search for artwork of a Dyson sphere and you will often see a star enclosed inside an enormous artificial shell. Sometimes the inner surface contains continents, oceans, cities, or habitats. In other illustrations, the sphere behaves like one unimaginably large solar panel built at planetary distance from its star. It is visually unforgettable. It is also a poor starting point for serious engineering. Freeman Dyson's famous 1960 paper was primarily an argument about observable energy use. He proposed that a sufficiently advanced civilization might convert a substantial amount of starlight into lower temperature radiation, and that astronomers could therefore search for unusual infrared emission associated with technological activity. The observational signature mattered more than a particular architectural blueprint. That distinction is important because a rigid spherical shell produces immense structural problems. Planets remain around the sun because they orbit. Earth is continuously falling toward the sun while moving sideways quickly enough that it continually misses it. The same principle applies to ordinary satellites and spacecraft. A connected shell is fundamentally different. Different portions of the structure could not independently occupy ordinary orbital trajectories while remaining joined into one rigid object. Instead, the entire shell would require support against enormous stresses. It would also face a positioning problem. A perfectly centered shell does not gain the kind of simple gravitational restoring behavior one might intuitively expect if the star shifts slightly relative to the structure. Maintaining alignment would require extraordinary control. A swarm avoids these problems by discarding the requirement that everything be connected. Imagine instead millions, billions, or eventually even larger numbers of independent spacecraft. Some might be extremely thin solar collectors. Others could be mirrors, manufacturing stations, habitats, computing systems, observatories, transport hubs, or radiator structures. Every unit follows an orbit. If one fails, the others continue operating. If more power is needed, more collectors can be added. If technology improves, newer generations can use different designs without requiring the existing infrastructure to be rebuilt. That modularity is one of the strongest arguments for a swarm rather than a shell. It also changes the construction problem. A solid sphere is difficult to imagine operating while half-built. A swarm is useful from the very beginning. One solar collector produces power. 10 produce more. 10,000 could support substantial industrial operations. At sufficiently large scales, solar infrastructure becomes an increasingly important component of an off-world economy. There is therefore no precise instant when space-based solar power becomes a Dyson swarm. The transition is largely one of scale, distribution, and purpose. A mature swarm would probably not consist of identical machines either. Real economies are heterogeneous. Cities contain homes, factories, offices, transport infrastructure, data centers, warehouses, hospitals, electrical systems, and many specialized facilities. A solar system civilization would likely develop the same diversity. Collectors close to the sun might be designed for extreme thermal conditions. Facilities farther away could prioritize computation or habitation. Mining centers might remain near resource-rich asteroids. Cargo vehicles would continually move between industrial zones. Some structures might collect sunlight directly. Others could concentrate it onto industrial processes. Some might transmit energy over distance. Many would simply consume power locally. The result would resemble an ecosystem of machines rather than one machine. That is what makes the Dyson Swarm a useful concept. It allows us to replace the need for fictional materials with many individual engineering questions based on familiar physics. We understand orbital motion. We understand solar cells. We know light transfers momentum. We know machines generate waste heat. We know automated systems experience failures. Nothing about those principles requires new physics. What changes is their scale. And once the solid shell is removed from the discussion, scale becomes the next major problem, because the amount of energy flowing outward from the sun is almost beyond ordinary intuition.
To understand why anyone might attempt a Dyson swarm, we have to stop thinking of the sun merely as the object illuminating Earth. It is an enormous power source. The nominal solar luminosity used by astronomers is about 3.828 times 10 superscript 2 watts. At Earth's orbital distance, total solar irradiance is about 1,361 watts per square meter before atmospheric effects. Those numbers immediately reveal the attraction. Earth receives only the sunlight that happens to intersect the planet's small cross-sectional area. Almost everything else continues outward. A Dyson swarm would intercept some fraction of that energy before it escapes into interstellar space. It would not need anything close to complete coverage to become extraordinary. 1/millionth of the sun's luminosity is roughly 3.8 times 10 superscript 2 watts. 1,000th is around 3.8 times 10 superscript 2 superscript 3 watts. 1% is approximately 3.8 times 10 superscript 2 watts. Even a tiny fraction of the sun's output would represent an energy economy vastly larger than anything humanity operates today, but collector area becomes equally astonishing. Imagine, purely as a reference, a sphere with a radius of 1 astronomical unit, the average Earth-Sun distance. Its surface area would be about 2.8 times 10 superscript 2 superscript 3 square meters. A real swarm would not be a continuous surface, but that figure tells us how much projected collecting area would be needed to intercept nearly all sunlight at that distance. 1% of that area would still mean roughly 2.8 times 10 superscript 2 1 square meters of collectors. Then comes the mass problem. If the complete collector system averaged 1 kilogram per square meter, full coverage at Earth's distance would require approximately 2.8 times 10 superscript 2 superscript 3 kilograms of material, comparable to the mass of Mercury. Reduce the aerial density to 100 grams per square meter, and the requirement falls by a factor of 10. At 1 gram per square meter, it falls by another factor of 100. This shows why reducing mass could be as important as acquiring more resources. A civilization capable of manufacturing extremely thin, durable structures would need far less mining, transportation, and processing for the same collecting area. Real spacecraft, of course, require more than an active solar layer. They need structural support, electronics, communication systems, sensors, thermal management, attitude control, perhaps propulsion, and equipment for deployment or maintenance. Every additional function adds mass. One strategy for reducing collecting area is to move closer to the sun. Solar intensity follows the inverse square law. At half Earth's distance, a surface receives roughly 4 times as much sunlight. Near Mercury's orbit, sunlight is several times stronger than it is near Earth. Move closer still, and the energy density rises rapidly. This provides 2 advantages. Each square meter can intercept more energy, and a spherical surface at the smaller orbital radius has less total area. For energy collection alone, the inner solar system can therefore look attractive, but the trade-off is thermal stress. More sunlight means higher operating temperatures. Materials degrade faster. Electronics require greater protection. Solar radiation pressure becomes more significant. Orbital velocity increases. Maintenance becomes more difficult. A collector designed for Earth's neighborhood might be completely unsuitable, very close to the Sun. There may therefore be no single ideal swarm radius. Different functions could occupy different regions. High-temperature solar collectors and industrial facilities might operate in the inner solar system. Habitats could remain farther away. Large computing installations might operate at distances where heat rejection is easier. Mining infrastructure could be distributed according to where resources actually exist. Instead of forming one tidy layer, a mature swarm might extend through a large fraction of the planetary system. It is also a mistake to assume that a civilization would necessarily attempt to capture every available photon. Perhaps 1% of the sun's power would already exceed practical demand. Perhaps environmental preservation would matter more than maximum energy extraction. Perhaps further construction would become economically inefficient. Or perhaps future technology would allow a civilization to achieve its goals with far less energy than the Kardashev framework implies. The scale describes energy use. It does not tell us what an advanced society would value. Still, the calculation explains why the Dyson idea remains compelling. The sun is already producing the energy. The engineering problem is how to place enough infrastructure in useful locations to intercept it, and every one of those machines must orbit. That turns the Dyson Swarm into an astronomical traffic problem.
Saying that a Dyson Swarm surrounds the sun makes the geometry sound much simpler than it really is. Every component needs a trajectory. Nothing simply hangs motionless beside the sun unless another force continuously supports it. A collector must move at a velocity appropriate to its distance from the star. The closer the orbit, the faster that motion becomes. Earth requires 1 year to complete an orbit. Mercury takes about 88 days. Objects substantially closer to the sun can complete their circuits in much shorter periods. The swarm is therefore never a stationary shell. It is an enormous system in continuous motion. One architecture could place many collectors along similar circular paths, spaced like moving beads around a ring. Another could use multiple rings at different orbital radii. Some spacecraft might use inclined trajectories that take them above and below the principal plane of the planets. A sufficiently developed system could contain thousands or millions of orbital families optimized for different tasks. Problems emerge where those trajectories interact. Two orbital paths can cross geometrically without producing a collision if their spacecraft pass the crossing point at different times. But as the number of objects increases, so does the number of potential close approaches that must be predicted. Modern satellite operators already track spacecraft and debris around Earth. A mature Dyson Swarm would require that capability at an almost unimaginable scale. Each major unit would need precise knowledge of its position and velocity. Navigation networks would project future trajectories. Nearby spacecraft would exchange maneuver plans. Local systems would coordinate changes long before two objects approach the same region. The swarm would require continuous computation simply to remain organized. Sunlight itself complicates this. Photons carry momentum. When light is absorbed or reflected, it exerts a small pressure on the surface it strikes. For heavy spacecraft, that effect is usually modest. For very thin structures with huge area and little mass, it becomes much more important. Solar sails already exploit this phenomenon deliberately. A Dyson collector could behave partly like a sail even if energy generation were its primary purpose. By altering its angle toward the sun, it could adjust the direction of radiation pressure and gradually modify its trajectory. That may be useful for station keeping. It could also cause navigation errors. A damaged surface could change reflectivity or orientation, producing an unexpected drift. Extremely lightweight infrastructure would therefore need radiation pressure included in every trajectory model. Shadowing creates another issue. When the swarm is sparse, one collector occasionally passing behind another is insignificant. As coverage grows, temporary eclipses become more common. Different inclinations, distances, and orbital phases could minimize unnecessary overlap. At very high density, however, the components begin interacting not only through collision risk but through radiation. Inner collectors absorb sunlight and later emit energy at longer wavelengths. Outer facilities could intercept some of that radiation. The system gradually becomes a complex radiative environment rather than a collection of independent solar panels. The planets remain part of the picture too. Earth, Venus, Mercury, Mars, Jupiter, and the other worlds do not disappear because industrial infrastructure has expanded. Their gravity affects nearby trajectories. Protected orbital zones may be needed. Habitats could require large safety margins. Astronomical observatories may need low-interference regions. Cargo spacecraft need predictable transfer corridors. Power transmission beams require clear paths. The solar system could therefore develop something resembling zoning. One family of trajectories might be dominated by power collectors, another by transport. Other areas could be designated for habitation, manufacturing, observation, or emergency maneuvering. Some regions might intentionally remain almost empty. This is difficult to visualize because terrestrial infrastructure is mostly stationary. A building has an address. A road occupies a fixed route. In a Dyson swarm, the factory moves. The solar station moves. The habitat moves. The cargo terminal moves. The transmission platform moves. Much of civilization becomes a choreography of predicted trajectories. Errors matter because relative velocities can reach many kilometers per second. Yet this problem is not inherently chaotic. Orbital mechanics is highly predictable when the forces are understood. In some respects, a carefully organized swarm could be more mathematically predictable than traffic on a crowded city street. The challenge is maintaining that predictability over enormous timescales as equipment ages, new infrastructure is added, solar radiation changes trajectories, and components occasionally fail. A civilization capable of managing this would have turned orbital mechanics into everyday infrastructure management. But orbital planning alone cannot create a swarm. The machines still need material. And that is where Mercury enters the discussion. Mercury appears frequently in Dyson Swarm discussions for understandable reasons. It is close to the Sun. It contains an unusually large metallic core relative to its size. It lacks Earth's oceans and substantial atmosphere. And its mass is enormous compared with any industrial project humanity has attempted. It is easy to imagine a future civilization operating automated mines across parts of Mercury, refining useful material with abundant solar energy, and launching manufactured components into heliocentric orbits. If that process continued far enough, an increasing fraction of Mercury's material could theoretically become part of solar system infrastructure. That image provides a simple narrative. A planet becomes the raw material for a technological system around the Sun, but complete dismantling is neither obviously necessary nor necessarily desirable. The first problem is composition. Total mass tells us surprisingly little about how convenient that material would be for particular technologies. Solar collectors may require one set of materials. Electronic systems require another. Conductors, radiators, motors, mirrors, sensors, and structural components all impose different chemical and manufacturing requirements. A world can contain huge quantities of matter while still making certain critical elements inconvenient to obtain. Then comes processing. Natural rock is not finished technology. It must be excavated, crushed, separated, chemically refined, purified, shaped, fabricated, assembled, tested, and integrated into functioning systems. Modern electronics require purity and precision far beyond simple metallurgy. If a civilization cannot perform those processes efficiently in space, a planetary supply of raw material does not automatically solve anything. Mercury's gravity also matters. It is weaker than Earth's. but it still takes substantial energy to move large amounts of mass away from the planet and place them into appropriate solar orbits. Removing enormous quantities would require extensive transportation infrastructure. For some materials, small asteroids could be more attractive precisely because their escape velocities are low. Many can be mined without climbing out of a deep gravitational well. They also differ in composition. Some are comparatively metal-rich. Others contain water-bearing minerals, carbon compounds, or silicates. Their usefulness would depend not only on what they contain but also on their trajectories. An ordinary asteroid already passing near an industrial region might be economically more valuable than a richer object requiring a major orbital change. That does not make the asteroid belt unlimited. It is extremely sparse, and the combined mass of its objects is small compared with a terrestrial planet. Asteroids could still supply an extraordinary industrial civilization while becoming insufficient for certain visions of near-complete stellar coverage. Resources also exist farther out. Moons, icy bodies, and other small objects contain water, carbon-bearing material, silicates, and metals. The question is whether the time and energy needed to transport them inward would justify the benefit. A realistic Dyson economy would therefore probably draw material from many locations. The Moon could help build early space infrastructure. Near-Earth asteroids could supply accessible resources. Parts of Mercury might become major industrial zones. The asteroid belt could support additional manufacturing. Outer system resources might become valuable for habitats, propellant, chemistry, and cold region industry. And preservation could remain an explicit choice. Mercury has scientific value as a record of the inner solar system's formation and evolution. A future civilization may decide that completely dismantling a planet is unacceptable even if it possesses the technical capability. Engineering capability does not determine cultural values. There is already a useful precedent for treating these resource questions as optimization problems. The Global Trajectory Optimization Competition's GTOC 11 challenge asked teams to design trajectories in a fictional Dyson ring construction scenario in which asteroid material was directed toward construction stations. The competition did not demonstrate that a Dyson structure is technologically achievable. It explored the difficult trajectory planning problem inside a highly idealized scenario. That distinction captures an important principle. The resource challenge is not simply finding enough mass. It is choosing which material to use, where to process it, when to move it, how much energy to spend moving it, and how to transform it into working infrastructure. A mountain of metal is not a solar collector. An asteroid is not a computer. The difference is manufacturing. And if billions or trillions of devices are ever required, conventional manufacturing capacity will not be enough. The industrial system itself must expand.
Manufacturing may be the central challenge of the entire Dyson Swarm idea. Imagine engineers create an excellent solar collector. It is lightweight, durable, efficient, simple to deploy, and capable of surviving years of exposure to the inner solar system. Now imagine humanity manufactures 10,000 of them. That would be an extraordinary achievement by present standards. At Dyson Swarm scale, it could still be almost negligible. If the eventual architecture requires billions, trillions, or more units, fixed manufacturing capacity becomes the limiting factor. Linear production scales too slowly. A factory that makes the same number of collectors every year will require twice as much time to produce twice as many collectors. For a project measured in astronomical areas and planetary quantities of material, that becomes impractical. The obvious solution is to expand production capacity while construction is underway. This is why self-expanding or partly self-replicating industry appears so often in discussions of megastructures. The basic mathematics is powerful. Suppose an industrial system can build enough additional equipment to double its productive capacity every 10 years. After 10 doublings, capacity is more than 1,000 times larger. After 20, it exceeds 1,000,000 times the starting level. After 30, it is roughly 1,000,000,000 times larger. In a simplified mathematical model, enormous growth can emerge from a relatively small industrial seed, reality is much harder. No fully autonomous factory today can reproduce everything required to build another copy of itself from raw local material. Modern factories depend on global supply chains. An automobile plant does not extract its own iron, refine its own copper, manufacture every machine tool, produce every semiconductor, assemble every industrial robot, and build all the equipment required to replace itself. Thousands of specialized facilities support it. A space factory aiming for genuine self-sufficiency would have to reproduce increasing portions of that industrial web. It must locate usable material, mine it, separate elements, refine them, manufacture parts, maintain tools, assemble machinery, test products, diagnose unexpected failures, and eventually produce advanced electronics and the equipment needed to manufacture those electronics. Semiconductor fabrication alone demonstrates how difficult industrial closure could become. The path toward self-sufficient space manufacturing would therefore almost certainly be gradual. Early lunar or asteroid facilities might produce simple bulk products, structural members, shielding, glass, oxygen, or uncomplicated mechanical parts. Sophisticated electronics would still arrive from Earth. Later, motors, wiring, sensors, optical components, and control equipment might be manufactured locally. Eventually, increasingly complex computing hardware could be produced away from Earth. At each step, dependence on imported material would decline. Perfect self-replication is not necessary. The more useful concept is industrial closure. If an off-world factory can produce 50% of the mass required to expand itself, it already reduces the burden on Earth. If it reaches 90%, the situation changes dramatically. At 99%, only a small fraction of the new facility must arrive from somewhere else. That could be enough to make rapid expansion practical. Automation is equally important. Communication delays make constant control from Earth impossible across much of the solar system. A mining robot cannot stop every few minutes and ask a human engineer what to do. Machines must identify routine faults, adapt to unexpected material properties, reroute work, maintain equipment, and coordinate with neighboring systems. Dust will enter mechanisms. Radiation will affect electronics. Tools will wear. Mechanical parts will fail, or composition will differ from predictions. A viable space economy must treat those conditions as normal operation. Self-expansion also needs safeguards. A manufacturing system capable of producing additional machines can reproduce design defects as efficiently as successful features. A flawed component could appear across thousands of facilities before engineers recognize the problem. Poorly controlled extraction could consume protected resources. A bad software update could propagate rapidly through industrial networks. Expansion would therefore require authentication, independent verification, version control, quality assurance, and clear limits on what machines are allowed to manufacture. Diversity could improve resilience. Different factories might use different architectures so that a single defect cannot disable every production center at once. A mature Dyson economy may consequently look less like an army of identical self-copying robots and more like a distributed industrial civilization. Mining centers specialize in extraction. Refineries purify material. Electronics facilities build control systems. Shipyards assemble transportation vehicles. Collector factories manufacture enormous areas of lightweight solar hardware. Repair stations recover failed equipment and return its material to the production cycle. Once such a network becomes sufficiently capable, expansion reinforces itself. More collectors produce more energy. More energy supports more manufacturing. More manufacturing produces additional collectors and factories. The important technological threshold may therefore be neither one revolutionary machine nor one spectacular launch. It could be the moment when civilization develops an off-world economy capable of reproducing most of its own productive capacity. Yet factories still need supplies. Those supplies may be scattered across hundreds of millions or billions of kilometers. Every kilogram is already moving through an orbit, so the next industrial revolution would have to occur in transportation.
Space is nearly empty, which can make transportation sound easy. There is almost no atmospheric drag. Once something is moving, it can continue moving for a very long time. But orbital transportation is fundamentally about changing velocity. Every asteroid, planet, station, and spacecraft already travels around the Sun on a particular trajectory. Moving cargo from one useful orbit to another requires changing that motion. Spaceflight engineers describe the required velocity change as delta V. In a mature space economy, delta V would behave almost like transportation cost. Two asteroids could contain almost identical resources yet have completely different practical values. One might already pass close to an industrial zone. The other could occupy a distant, eccentric, or steeply inclined orbit that requires far more energy or time to reach. Dyson Swarm builders would therefore care about accessibility as much as composition. Chemical rockets provide high thrust but consume propellant rapidly. Electric propulsion can use propellant far more efficiently but accelerates slowly. Solar sails obtain momentum from sunlight without conventional propellant. Electromagnetic launch systems could propel processed material from low-gravity bodies. Gravity assists might help selected cargo trajectories exchange momentum with planets. No single system is likely to dominate every task. Heavy cargo traveling slowly may use one method. Human transportation could use another. Lightweight collectors might use another still. For bulk material, speed often matters less. An industrial project planned decades in advance can tolerate a shipment requiring years to reach its destination. Rock does not care whether the journey takes 9 months or 12 years. That makes extremely efficient low-thrust propulsion more attractive. Solar sails could be particularly useful for lightweight manufactured structures. In some concepts, a collector could double as its own sail. It could be fabricated near a resource site, deployed, and gradually navigate toward its operational orbit using sunlight. Heavy raw material is more difficult. One option is to process resources near the asteroid and transport only refined products. That reduces transportation mass but demands sophisticated industrial equipment at the mining site. Another option is to move larger quantities toward centralized processing hubs. That simplifies some manufacturing but increases transportation requirements and operational risk. Moving a large object through the inner solar system would demand conservative trajectory planning. A navigation error involving substantial mass could create unacceptable risk for inhabited regions or critical infrastructure. The safest architecture would likely include protected corridors, multiple layers of trajectory verification, and strict limits on approaches to populated zones. Large shipments could be divided into smaller units. Emergency propulsion might provide additional margin. Certain trajectories might simply be prohibited. At that stage, the Dyson Swarm becomes less like a single construction project and more like an economy. Resources flow along routes. Depots hold material. Tugs move cargo. Energy stations support transportation systems. Navigation networks forecast positions years ahead. Industrial planners decide whether a resource should be processed locally, transported elsewhere, or ignored. A body containing valuable material may still be uneconomic if accessing it consumes too much time, energy, or transportation capacity. The solar system becomes a landscape of transfer costs. Different regions could specialize. The inner solar system offers intense sunlight and proximity to many potential collector orbits. The asteroid belt offers a diverse collection of accessible small bodies. Outer regions provide large inventories of volatile materials and colder environments that could be valuable for certain industries or computing systems. Cargo routes could connect these specialized zones. None of this requires faster-than-light travel. It requires automation, precision, patience, and equipment capable of remaining reliable over long missions. As traffic increases, however, each cargo vehicle becomes another moving object sharing the same enormous orbital environment as collectors, factories, observatories, habitats, and planets. Transportation therefore merges with traffic management. The civilization has to learn not only how to move vast amounts of material through space, but how to ensure that every shipment remains predictable. At maturity, a Dyson Swarm could contain so many independently moving objects that the word traffic barely captures the problem. Collectors orbit, factories orbit, habitats orbit, cargo vehicles orbit, repair craft, radiators, communications platforms, observatories, and navigation beacons all move as well. Near the Sun, orbital velocities can reach tens of kilometers per second and, at sufficiently small distances, more than 100 kilometers per second. At such speeds, even relatively small objects possess substantial kinetic energy. A collision could create fragments that enter their own heliocentric trajectories. Those fragments might later intersect other operational regions. This does not mean a well-designed swarm inevitably becomes an uncontrolled debris environment. Space is enormous. Separated orbital families can remain orderly. The challenge is preserving that order for centuries while infrastructure grows and individual machines occasionally fail. Every important object would probably contain precise navigation equipment. Regional sensors would continually update orbital information. Unresponsive spacecraft could be tracked externally. Prediction software would identify close approaches far in advance. Automated maneuvering systems could make small corrections before those encounters become urgent. The principle resembles today's spacecraft traffic management, but extended across a solar system and multiplied by enormous numbers of machines. Communication delay makes centralized control inadequate. Depending on orbital positions, parts of the solar system are separated by minutes or hours of light travel time. An urgent local maneuver cannot always depend on a controller somewhere else receiving a warning and sending instructions back. Autonomy becomes unavoidable. Each region must be capable of managing routine navigation locally. Spacecraft would need to recognize hazardous instructions, communicate with neighboring units, negotiate trajectory changes, and execute predefined safety procedures. That creates a direct connection between orbital engineering and cybersecurity. A false command could create serious operational hazards. A compromised cargo system could place valuable infrastructure at risk. A faulty software update could affect thousands or millions of machines simultaneously. Strong authentication would therefore be part of flight safety. Critical trajectory changes might require independent verification. Navigation systems could be isolated from less secure networks. Different regions might intentionally use different software or hardware architectures so that one vulnerability cannot spread everywhere. Scale makes reliability even more important. Suppose a swarm contains 1 trillion active units. Even an annual serious failure rate of only 1 in a million would still produce 1 million failures every year. Breakdown cannot be treated as an exceptional emergency. It has to be an ordinary industrial process. Some spacecraft could be repaired. Others might be designed for rapid replacement. Failed collectors could transition automatically toward designated disposal trajectories. Repair stations could recover valuable components. Recycling facilities could process equipment that no longer justifies maintenance. The safest machine may be one that becomes predictable and harmless when it fails. Orbital zoning could reinforce that strategy. Dense collector regions might use carefully standardized trajectories. Freight corridors could occupy separate inclinations. Habitats might receive wider exclusion zones. Some orbital bands could remain intentionally sparse to provide emergency maneuvering space. The solar system would develop an invisible geography defined by both position and velocity. This is the idea of phase space. On Earth, two objects are generally considered separate if they occupy different locations. In orbital mechanics, location alone is not enough. Two spacecraft can safely pass through the same region at different times. Two spacecraft currently millions of kilometers apart may still be headed toward a future close approach. Prediction matters as much as present distance. Diversity matters too. One universal collector design might simplify manufacturing, but uniformity creates common failure modes. A radiation vulnerability, material flaw, or software bug could affect enormous numbers of identical units. A resilient swarm might intentionally use multiple designs and control systems. Redundancy would therefore exist not merely within machines but across the civilization's architecture. Then comes governance. Who receives access to a particularly valuable orbit? Who has priority in a congested transfer corridor? Who is responsible when malfunctioning equipment creates risk for another operator? Who defines navigation standards? Who has authority to order emergency maneuvers? Those may sound like political questions, but at this scale they directly affect engineering reliability. A mature swarm would need more than machines orbiting the sun. It would require trustworthy systems capable of coordinating astronomical numbers of partly autonomous machines despite long communication delays. In effect, civilization would need an operating system for the solar system, and that raises another question. What is all this infrastructure actually going to do with the energy it collects?
A Dyson Swarm is usually introduced as an energy-harvesting megastructure, but energy only matters when there is something useful to do with it. That point changes how we should picture a Type 2 civilization. A mature swarm would probably not feed electricity into one enormous civilization-wide electrical grid. The distances are too great, and transmitting energy is never perfectly efficient. Much of the power would likely be consumed near the location where it is collected. A solar station near the sun could directly support nearby manufacturing. Mirrors might focus solar energy onto industrial furnaces. Mining operations could run electromagnetic launch systems. Habitats could rely on local collector networks. Computing installations could operate beside dedicated power sources and radiators. Local use avoids the need to move staggering amounts of energy across the system. When long-distance transmission is useful, lasers and microwaves offer possibilities. Both propagate efficiently through vacuum, but neither produces a perfect wireless power network. Diffraction causes beams to spread. Long distances require large transmitters, large receiving apertures, short wavelengths, or some combination of all three. Pointing accuracy becomes critical because both transmitter and receiver are moving. The beam must be aimed not merely at where the target is when transmission begins, but where it will be when the energy arrives. Beam paths also need to avoid unrelated infrastructure. High-power transmission systems would require multiple safety layers. Protected directions could be defined. Transmission might occur only when several independent navigation systems confirm that the receiver and surrounding corridor are clear. Populated regions could have strict power limits. Different frequencies might be assigned to different applications. These complications favor local energy economies. A mature Dyson Swarm may resemble countless interconnected but semi-independent grids rather than one gigantic power station. What could consume stellar-scale energy? Computation is one possibility. Advanced civilizations could perform vast scientific simulations, operate enormous artificial intelligence systems, model physical phenomena at extraordinary resolution, or support digital environments inhabited by large populations. Industry is another. Energy could drive refining, manufacturing, particle acceleration, propulsion, and large-scale materials processing. Enormous laser systems might accelerate interstellar probes. Artificial habitats could support populations far beyond the capacity of one planet. Scientific infrastructure could become equally ambitious. Imagine telescope arrays with baselines stretching across millions of kilometers, or particle experiments that could never fit on a planetary surface, or observatories positioned throughout the solar system to study the universe from many wavelengths and vantage points. Energy might also be used to alter asteroid orbits gradually, manage planetary environments, or support long-term space engineering. But abundant energy does not create unlimited capability. A civilization with 10 times more power is not automatically 10 times more intelligent, organized, or scientifically advanced. Energy is one constraint among many. Material, information, knowledge, coordination, and time remain essential. This reveals one limitation of the Kardashev scale. Energy use is valuable because physics places hard constraints on what energy can accomplish. But power consumption alone cannot describe every dimension of technological sophistication. A civilization that accomplishes more with less energy could be more advanced in meaningful ways than one that consumes enormous amounts inefficiently. A Dyson Swarm, therefore, need not be an inevitable destination. Growth may continue only while additional collecting capacity provides sufficient benefit. Expansion might stop at 1/1,000,000th of the Sun, or 1%, or 10%. Natural environments might be deliberately preserved. Different societies within the solar system might pursue completely different technological strategies. A mature system may not even behave as one unified civilization. Future technological advances could also change demand. More efficient computation reduces energy use. Better materials reduce manufacturing requirements. Improved propulsion changes transportation economics. The architecture we imagine today may therefore look little like the infrastructure actually chosen by a distant future society. One physical requirement, however, remains. Almost every ordinary use of energy ultimately generates heat. Computers warm up. Factories warm up. Habitats warm up. Electrical systems warm up. If a civilization captures a substantial fraction of the sun's luminosity, it must eventually deal with an equally extraordinary thermal problem. Collecting energy is only half the story. The other half is releasing it again.
Unlimited solar energy sounds almost effortless. The sun is already shining. Collecting energy does not require creating the source. But once a civilization begins intercepting stellar-scale power, a deeper constraint appears. Energy does not simply vanish after being used. A collector absorbs sunlight and converts some of it into electricity, mechanical work, computation, chemical processing, or propulsion. Eventually, much of that useful energy becomes heat. On Earth, heat can move through air, water, soil, cooling systems, and eventually the atmosphere and space. In vacuum, a spacecraft cannot rely on convection into the surrounding environment. It must ultimately radiate heat away electromagnetically. Radiators therefore become fundamental Dyson Swarm infrastructure. Every habitat, industrial plant, computer installation, and power system needs a thermal pathway. Radiator performance depends strongly on temperature. Hot surfaces can radiate much more power per unit area than cold ones. That creates a trade-off. Operating machinery at high temperatures can reduce radiator area, but the equipment must tolerate those conditions. Operating at lower temperatures may benefit certain electronics, computing systems, or inhabited environments, but larger radiators are required. Different applications could therefore occupy different thermal zones. High-temperature industrial equipment might operate relatively close to the sun. Habitats may prefer more moderate regions. Certain computing systems could operate farther away if cooler surroundings improve their efficiency enough to justify the distance. The best location for collecting sunlight is not necessarily the best location for using the resulting energy. That could make a mature swarm much more spatially extended than the classic image suggests. Waste heat has another consequence. It makes technological energy use potentially observable from interstellar distances. Dyson's 1960 argument focused on this possibility. Starlight absorbed by a technological civilization would ultimately be re-emitted at longer infrared wavelengths. That does not make infrared excess evidence of technology by itself. Nature produces infrared radiation extremely easily. Dust around stars absorbs shorter wavelength light and re-emits it in infrared. Young stellar systems contain dusty disks. Evolved stars can be dusty. Background galaxies can overlap the line of sight. Active galactic nuclei can also be intense infrared sources. Every candidate therefore requires careful follow-up. This difficulty has become especially clear in recent searches. Project Hephaestus analyzed optical and infrared observations from millions of stars and identified a small number of unusual objects worthy of additional investigation. Subsequent work showed that background sources can mimic the expected infrared signature. High-resolution observations identified background galaxy contamination in multiple cases, and JWST observations reported in July 2026 found that the excess associated with 2 additional candidates came from background galaxies rather than structures surrounding the stars. No Dyson Swarm has been confirmed. That is not a failure of the search. It demonstrates how science progresses. Potential anomalies are identified. Alternative natural explanations are tested. Better instruments eliminate false positives. Each result improves future search techniques. Thermal engineering also affects what a genuine technological system would look like. A relatively hot swarm would emit strongly at shorter infrared wavelengths. A civilization using enormous cooler radiators might shift much of its waste heat to longer wavelengths. Different designs produce different astronomical signatures. From a distant telescope, thermal architecture could become part of a civilization's observable appearance. Waste heat also limits computation. Abundant energy cannot support limitless computing inside a tiny volume. The heat generated by that computation must leave somehow. For a civilization interested in enormous processing capacity, radiator manufacturing could become as important as processor manufacturing. This means the familiar artistic image of a Dyson swarm made almost entirely from solar panels may be misleading. An enormous fraction of its physical area could be devoted to thermal management. The sun provides an extraordinary supply of energy. But thermodynamics still applies. The swarm does not escape physical limits. It reveals those limits on stellar scale. And when infrastructure reaches that scale, reliability becomes equally important. The environment surrounding the sun is not gentle. Solar radiation, energetic particles, thermal cycling, micrometeoroids, mechanical wear, and long periods without direct maintenance all affect spacecraft. Infrastructure close to the sun faces even more intense conditions. Ultraviolet exposure can degrade materials. Charged particles can disrupt electronics. Extreme temperature cycles can weaken structures. Thin surfaces can be punctured. Mechanical systems eventually wear. Software encounters situations its designers did not anticipate. Any realistic Dyson swarm must therefore assume that failures occur constantly. That expectation favors distributed architecture. If one collector stops functioning, the rest of the swarm can continue operating. A repair craft might recover it. If repair is uneconomic, its material could be recycled. The goal is to make individual failures routine rather than system-wide events. Scale makes this essential. Even extraordinarily reliable technology produces many failures when deployed in astronomical numbers. 1 trillion operating units with an annual serious failure rate of just 1 in a million would still create 1 million failures per year. Human repair missions could never handle that workload. Maintenance must be automated. Some components could be engineered for long service lives. Others might deliberately be cheap and replaceable. A civilization could compare the resources required for repair with those needed to recycle an old unit and manufacture a new one. The same trade-off applies to radiation protection. Instead of adding heavy shielding to every thin collector, it might be more efficient to accept gradual degradation and replace exposed surfaces periodically. Solar activity would require additional resilience. Sensitive equipment could enter protective configurations. Collectors might alter orientation. Redundant electronics could take over after faults. Critical information could be stored across multiple locations. Important facilities could use thick shielding made from locally available rock or metal. When material is abundant, mass itself can become a practical form of protection. Information failures may be even more serious than hardware failures. A navigation bug distributed to billions of spacecraft could create widespread trajectory errors. A faulty manufacturing specification could generate defective components across many factories. A compromised control network could issue inappropriate commands to powerful equipment. Diversity, therefore, becomes another safety strategy. Different regions could use different processors, control software, manufacturing methods, and navigation implementations. That creates inefficiency. It also reduces the chance that one flaw affects every component simultaneously. Biological ecosystems gain resilience from diversity. A technological ecosystem spread across a solar system may benefit from the same principle. Governance becomes a form of engineering too. Who has permission to alter the trajectory of a large asteroid? Who authorizes high-power transmission across busy orbital regions? Who is responsible for uncontrolled equipment? Which orbital zones are protected? Who resolves disputes over navigation priorities? These questions influence physical safety. A poorly designed institution can create risks just as surely as a poorly designed machine. A Dyson-scale civilization could therefore require layers of coordination. Individual spacecraft handle immediate navigation. Local networks organize nearby traffic. Regional organizations manage transport and industry. Wider standards govern resource extraction, communications, and high-energy operations. Emergency systems could temporarily override ordinary commercial activity when traffic conditions demand it. The greatest concern would be cascading failure. One malfunction affects nearby infrastructure. Automated responses create additional problems. Power becomes unavailable to a region. Maintenance capacity becomes overloaded. A resilient architecture has to prevent those chains from spreading. Orbital separation can act as a firebreak. Independent communication networks can limit propagation. Critical facilities can maintain local energy storage and redundant supply routes. Important manufacturing systems can be distributed across multiple regions. The goal is preventing one local problem from spreading across the solar system. There is also another possibility. Expansion eventually stops. Perhaps convenient resources become less attractive. Perhaps maintenance absorbs an increasing percentage of industrial output. Perhaps additional energy is no longer valuable enough to justify the complexity. A stable partial swarm could ultimately be more useful than a continuously expanding one. That challenges the assumption that advanced civilizations must always pursue maximum energy capture. More infrastructure creates more capability. It also creates more maintenance, traffic coordination, and responsibility. Success may therefore mean something other than surrounding the entire sun. It may mean building a stable technological ecosystem capable of operating for thousands or even millions of years. Which leads directly to one of the hardest questions of all. How long would something like this take?
Any prediction that humanity will complete a Dyson swarm in a particular century should be treated cautiously. We do not know whether humanity will ever attempt such a project. We do not know what future collectors would be made from. We do not know how light they could become. We do not know what resources would be economically attractive. We do not know how autonomous manufacturing might develop. And we do not know what fraction of the sun's energy a future civilization would actually want. With uncertainties that large, there is no single meaningful completion date. What we can identify are the variables that control the timescale. The first is the target coverage. Capturing 1/1,000,000th of the sun's output is a completely different industrial project from intercepting half of it. The second is mass per unit area. Lightweight collectors reduce mining, refining, transportation, and manufacturing requirements. The third is industrial throughput. A space economy processing millions of tons annually is fundamentally different from one capable of processing quantities many orders of magnitude larger. The fourth is the growth rate of manufacturing capacity itself. Fixed production produces essentially linear expansion. Self-expanding production changes the mathematics dramatically. Suppose an industrial network doubles its productive capacity every decade. After 10 doublings, output is roughly 1,000 times greater. After 20, roughly 1,000,000 times. After 30, roughly 1,000,000,000 times. Under a perfectly idealized model, only about 3 centuries separate the original system from a 1,000,000,000-fold increase in capacity. That is why expanding space industry is so important to Dyson Swarm discussions. It creates a mathematical path from modest infrastructure to enormous scale without requiring the first generation to construct everything itself. But real industrial growth will never remain perfectly exponential. Convenient resources are used first. Transportation systems become more complicated. Maintenance requirements grow. Specialized materials create bottlenecks. Radiator construction consumes resources. Equipment reaches the end of its service life. Some production capacity must be devoted to replacing existing machines rather than building new ones. Social decisions can slow expansion or redirect investment. Eventually, growth must flatten. The interesting question is how much infrastructure can be built before that happens. One possible development pathway begins close to technologies we already recognize. Human activity expands around Earth and the Moon. Lunar resources provide shielding, oxygen, water, and construction material. More hardware is assembled directly in space. Asteroid missions progress from reconnaissance to increasingly capable extraction. Solar energy supports a growing percentage of off-world operations. Earth continues exporting complex electronics and specialized machinery. Over time, manufacturing capability spreads outward. Simple structural products come first. Then motors, sensors, optical equipment, power electronics, and precision machinery. Eventually, advanced computing hardware is produced beyond Earth. Industrial closure gradually increases. The solar system begins to contain factories capable of manufacturing most of the mass required to build additional factories. Only after that threshold does rapid expansion become plausible. The earliest stages could therefore be the hardest. Creating the first mostly independent asteroid refinery may require more innovation than manufacturing the millionth standardized collector. Building the first advanced semiconductor facility away from Earth could be more difficult than expanding an already mature industrial network by another %. Infrastructure makes additional infrastructure easier. The first centuries of a Dyson-scale trajectory might therefore be spent mostly building the ability to build. Initially, solar collectors would remain insignificant relative to the eventual scale. Then a threshold could be crossed. Industrial nodes begin producing new industrial nodes without substantial dependence on Earth. Mining spreads. Transportation capacity grows. Collector production accelerates. More energy supports more industry. Expansion becomes self-reinforcing. So how long would a Dyson swarm take? Under aggressive assumptions about automation and industrial growth, substantial stellar-scale infrastructure might emerge over centuries. If expansion is slower, thousands of years are easy to imagine. If civilization repeatedly pauses, changes priorities, or pursues only partial coverage, development could continue for far longer. The uncertainty spans many orders of magnitude. The important point is that known physics does not obviously require a timescale comparable with the age of the universe. The obstacles are primarily technological, economic, industrial, organizational, and social. That places Dyson swarms in an interesting category. They are not known to be prohibited by fundamental physics. They are also far beyond anything humanity can presently construct. There would probably be no single invention called the Dyson swarm. Instead, progress would require advances in robotics, autonomous manufacturing, materials science, orbital transport, thermal engineering, power systems, computing, and governance. If those capabilities never emerge, the swarm remains a thought experiment. If they do, expansion might occur gradually enough that nobody can identify the exact year construction began. And once a civilization learns how to industrialize one planetary system, almost independently of its original planet. The relationship between a Dyson Swarm and a Type 3 civilization becomes easier to understand.
A Type 3 civilization sounds almost incomprehensible because a galaxy is so large that familiar forms of coordination stop working. The Milky Way is roughly 100,000 light-years across. A message moving at the speed of light takes thousands or tens of thousands of years to cross substantial portions of it. No central administration could make real-time decisions for an entire galactic civilization. No construction team leaving one planet could personally oversee industrial development around every star. Expansion on that scale would need to be distributed, and a mature Dyson Swarm would already require many of the same capabilities. To industrialize one planetary system, a civilization must learn how to mine distant resources, operate autonomous factories, maintain machines without constant supervision, coordinate enormous numbers of independent systems, and reproduce industrial capacity from local material. Those capabilities are also useful for interstellar settlement. A spacecraft traveling toward another star would not necessarily need to carry a finished civilization. It could carry the machinery, information, biological resources, and manufacturing tools required to establish one locally. Imagine a probe or settlement vessel reaching a nearby stellar system. It surveys the available planets and asteroids. It identifies useful resources. Mining begins. The first industrial machines manufacture additional equipment. Refining capacity expands. Solar collectors provide energy. Factories become increasingly capable. Eventually, the new system develops enough industrial independence to construct its own interstellar spacecraft. Some of those spacecraft travel onward. The process branches. One established system produces several new industrial seeds. Those systems later create additional ones. Conceptually, this resembles the expansion of factories inside a Dyson Swarm, except that the distances are measured in light-years instead of astronomical units. Real galactic expansion would not follow a perfect exponential curve. Stars are separated by different distances. Systems contain different resources. Equipment fails. Travel times vary. Civilizations change goals. Some settlements may prefer isolation. Others could become politically or culturally independent. Light-speed communication delays would make uniform control increasingly unrealistic. But distributed reproduction of technological ecosystems provides a possible route from one star to many without requiring centralized coordination. That may be the deeper importance of a Dyson Swarm. Its significance is not merely that it captures extraordinary energy. It could represent the stage at which civilization learns how to reproduce sophisticated industry far from its birthplace. Once that capability exists, moving to another star becomes primarily a problem of propulsion, reliability, and time rather than the need to reinvent an entire economic system. Even then, a Type 3 civilization would not necessarily cover every star with dense collectors. The Kardashev scale describes energy use. It does not prescribe architecture. A galaxy-spanning society might exploit only a fraction of the energy available in most systems. It might value efficiency more than maximum consumption. Could concentrate computing around certain stars. It might use compact objects or other energy sources. Many planetary systems could remain mostly untouched. That would make such a civilization less visually obvious than the classic picture of an entire galaxy filled with dimmed stars. Searching for it would still be difficult. Waste heat remains one possible technosignature because thermodynamics applies regardless of who builds the technology. But natural astrophysical sources can imitate infrared anomalies. Modern searches illustrate exactly how careful astronomers must be. There is currently no confirmed Dyson Swarm. There is no confirmed Type 3 civilization. That absence does not tell us whether such societies are impossible, extremely rare, distant, temporary, or simply different from the systems we know how to search for. The Dyson thought experiment remains valuable even if no extraterrestrial civilization ever builds anything resembling our imagined swarm. It forces us to think of civilization as a physical process. Energy must come from somewhere. Material has to be extracted and organized. Machines have to survive their environment. Information has to travel through networks. Heat must eventually be released. Transport must respect orbital mechanics. Interstellar communication cannot exceed the speed of light according to known physics. Greater intelligence does not remove those constraints. Greater scale makes them more important. And that may be the strongest connection between the Dyson Swarm and the Type 3 idea. The path from a planet to a galaxy may not consist of a sequence of gigantic monuments. It may instead be a gradual improvement in the ability of technological ecosystems to reproduce, repair, adapt, and coordinate themselves over ever greater distances. From several light-years away, a mature Dyson Swarm might look like one enormous megastructure around a star. From inside it would be nothing of the kind. It would be mines, factories, habitats, power stations, radiators, cargo networks, observatories, computer systems, repair fleets, and countless autonomous machines operating throughout an entire planetary system. The swarm is not really one object. It is civilization itself becoming large enough to treat a star as infrastructure. If that civilization eventually reaches other stars, the pattern can repeat. One industrialized system becomes several. Several become hundreds. Hundreds become thousands. For immense spans of time, a local engineering challenge becomes an interstellar one. And eventually, perhaps, a galactic one. A Dyson Swarm may be among the largest engineering projects compatible with known physics. But its greatest difficulty is not the size of any individual structure. It is everything that must exist before construction on that scale becomes possible. Autonomous mines, space-based factories, reliable orbital transportation, intelligent traffic management, vast thermal systems, repair and recycling networks, a distributed resource economy, and institutions capable of coordinating machines whose actions can matter across an entire planetary system. From far away, all of that might resemble one megastructure surrounding the sun. Up close, it would look like an entire civilization in motion. And perhaps that is the real lesson of the Dyson Swarm. Humanity would not reach that scale simply by becoming better at building large objects. We would first have to become capable of living, manufacturing, maintaining infrastructure, and surviving throughout the solar system. Only then would the transition toward a truly stellar civilization begin. And only after mastering that challenge could the path toward something even larger, a civilization spread among the stars, start to look imaginable.